do anything. Then I go here. So we are currently recording. I'm recording this lecture. So maybe you take this into regard with what you're going to say. Yeah, welcome to the first lecture in parallel and distributed programming or computing in the year 2024. And now let me see whether this actually does anything. Yes, okay. Okay, there is, as I just introduced, there is a book. I have it here, and there is a link, hopefully, to the Springer link. So when you're in the network of the university, you can look into the book, but it's the German version of the book because we don't have the access to the English version of the book for whatever reason. I don't know. So today we'll start with some theory and a little bit background, and I guess I will probably bore some of you because in order to get everybody on the same page, I start from more or less the beginning. Yeah, so we'll probably getting more interesting with time going on. Yeah, so we'll start with a question: Why would we study parallel programming in the first place? And for this, we look at the development of computers. So you probably know that computers become exponentially faster and faster, which usually means they grow by a fixed percentage, yeah, with speed and capacity per year. And this can be viewed in some detail by looking at the annual increase in compute power. So we probably all know it increases, but it increases in different ways. So their computers do different things. For example, they have an integer operation, which is usually regarded as the control structure. So they grow 55%. Are you well? Per year? And let me draw a very small picture here. Say we have a processor here, and the processor, so this is kind of a black box, and inside this black box there is a control unit. Could say this is a black box in the black box. Yeah? And this control unit is the thing that does integer operations. Yeah? It's usually used to keep track of the operations. And then there is something that is important for scientific computing, and this is the floating point operations. So when I was your age, computers did not necessarily have a floating point unit. So computers work also without floating point units because you can just use the control unit, the integer unit, to mimic. Yeah. So you can write a program that does floating point operations without the floating point unit, yeah, but this is of course no longer the case. This actually grows very quickly with 75% per year, and this is another unit. This is called the arithmetic. Okay, I always have to apologize in the first lecture that I'm very dyslexic. This is also proven by, oops, okay, no, this was not my dyslexia. Okay, so I'm going, so there's an arithmetic unit. Okay, when I'm writing nonsense or I'm writing things wrong, yeah, just correct it yourself. Is probably I'm going to do this. So there's an arithmetic unit. In the arithmetic unit, this does the floating point operations. So this is the processor, and in addition to the processor, there's something that we call the bus. And there is, of course, the memory. Okay, so this is very minimalistic picture of a computer, right? So, and integer and floating point operations, this is what happens inside the CPU, but the entire, time that, or the entire compute power is of course also influenced by the memory, in particular the capacity of the memory. So we have memory capacity. Memory capacity. So memory capacity is actually growing quite quickly. Yeah, so we'll have more and more memory, 60% more per year. And then, so this is basically what we have down here. And the one thing that is missing is the memory access time. So let's give me an idea. What do you think? The growth rate per year, memory access time? Given these other numbers? 40%. 40%? So we make this, so I have 40? 80? 80?
I think it's less than 40.
You think it's less than 40, and you think it's 80. Okay, so it is, according to my notes, see, I picked them up by another lecture. I'm not completely sure that these numbers are completely correct, but it's also not the point. The point basically is that we see this increase, this big increase in floating point operations, and we see a relatively big increase in memory capacity. Yeah, so it looks like we can do more and more and more with more and more memory, but there is one important thing in between, and this is the memory access time. And this is the big problem in computing in general, and of course in scientific computing. Nowadays, this is also something that we more or less understand, but I still remember the time when these things were a big mystery, and you see, you got your processor faster and faster and faster. Yeah, so I come from the time when every year we heard that the clock frequency of the computer got higher and higher and higher. What clock frequency do you have? And nowadays nobody knows what clock frequency they have in their computer. I don't know what clock frequency this computer has. I don't care. Yeah, so they basically have stopped increasing. You have a higher clock frequency, you get more floating point operations, probably more integer operations. Yeah, but it doesn't help you because you have the problem with the memory access time, which grows slower than the memory and the floating point and integer operation capacity. this leads us to something that is called the data starvation crisis. Sometimes also called the memory wall. Memory wall. And this is the problem that the compute capacity, so the capacity to actually do computations, this grows much faster than the memory access time. And this has very significant consequences on how we see programming and how we do computation in general. Yeah? So basically, the way computation, the programs that were the fastest 20 years ago are not necessarily fast today. Yeah? Because 20 years ago, the big problem was to do the actual computation. They said memory access is for free. Yeah? So they didn't care about memory. There was no cache. Yeah? By the way, what does RAM mean? RAM. Random access memory. So what does it mean? You can just address any point in this memory, and it all takes the same time. So this was the idea, right? We still call this stuff RAM, but it's no longer true that accessing any point in the memory has the same speed, yeah? Because we introduced caches, yeah? We have several memory banks. So back then, memory access basically for free, computation expensive. Nowadays, computation more and more and more is getting for free, and memory access is the thing that costs money. And this has these consequences on how we deal with our stuff. So the time to solve a problem is increasingly governed by memory access time. So this we always have to have in our mind, and now this can either become a bigger problem when we compute things in parallel, or parallel computing can help us. The bottom line is that we have to be aware of our hardware layout in our way we program we do our programming parallelization. I don't know whether I can break it like this. Parallelization. So this can either worsen or mitigate this problem. Worsen. The data starvation. Sorry, I'm not very familiar with the software. I'm trying, oops. Can I, yes. Okay. Now this is one of the problems that we want to solve, and now we look at the possibilities that we have. So we can now come to the actual parallel machines, and for this we have a machine classification. Classification by a guy called Flynn. And this is from I don't know what his name was, but it's Flynn. And this was published in IEEE Transactions on Computers. C21, number 9, and it's from 1972, so even before I was born. Yeah, so it hasn't really changed. Also, this book here, Parallel Programming, is also old, but yeah, some things don't change. So there is 4 different kinds of machines that we distinguish, and they are all named like this and pronounced in a little bit a strange way. SISD, yeah, I believe it's pronounced SISD. I would actually say SISD, but this is not how people pronounce it. SISD is called Single Instruction Single Data. So is everybody familiar with this thing, or is this still new? I don't. Then there is multiple instruction, single data, MISTI. Multiple instruction. Single data. Then, of course, there is single instruction, multiple data. It's actually something useful. Single instruction, multiple data. And then there is, of course, multiple instruction, multiple data. So it's just a matrix, yeah? Okay, let's look at these machines. So how would they look like? So the one that is the simplest and was the one that was common, of course, back then in the 70s. This is the classical single core machine. The classical single core machine has, of course, no relation to parallel programming or parallel computing. It's just a sequential machine. So it's not parallel at all. And it looks like this. So we have data, which of course will be somewhere in the memory. Then there is a processor. and this processor interacts with the data, and then there is a program in, I guess in American English would be with 1M. So, and I mean, some of you will probably know that there are other classifications of computers. There are von Neumann computers and other computers where you distinguish where you store data and the program, right? So the computers that we have nowadays, they have a common memory for data and program, but in different areas of the same memory, right? So so usually the program and the data would be somewhere in the memory shared together, but this is not that kind of classification we are dealing with here. So here we distinguish what is here actually parallel, and here everything is sequential. We have one processor, we have one set of data, and we have one program. And this is the classical single core machine. So this was SysD. Then comes MISTI. MISTI is a strange thing. So we have data. We have data here, and then we have multiple, so we have an interaction with multiple processors. Say this is processor 1, and down here we would have processor n, say, because there could be arbitrary many in between. It could be just 2 or it could be more. And they are both run by the same program. No, sorry. No. What did I say? Sorry, don't stop writing. Of course not. So they are run by different programs. Okay, this is a bit strange. This is why I made this mistake here. So they are run by one program and another program. Okay. What is this good for? So what happens to the data when the programs are not similar? Programs that are not similar can be. There's one program running here and another program running there. Yeah, so there's only one data.
I can think of examples for that, it's true. But this one's what like 2 different programs can do.
Yeah, so there are 2 different programs running on the same data.
Maybe.
So they have to agree somehow, right?
I'm sorry.
They have to agree because they have only one data. This is strange. So usually this kind of thing is usually not very useful for the stuff that we try to do. But there is or may be, at least there may be an application for this. So it's not used in scientific computing. Usually, I would say usually, because sometimes it could still be. But it has applications in fault tolerance. So they have to agree. Which means you can, you probably want to, let's say you have an atomic power station, right? And you want this thing to run not to fail, right? So then there's something here is keeping the temperature. Yeah? So you may have a specification for something that you want to control. This should be controlled like this, but it always has to work. Yeah? So what you could do is you have two separate programmers writing two programs independently that do the same thing. Yeah? You run both programs in parallel, and they should, do the same thing, and they would obviously recognize if they don't agree and give you a fault. Right? So this is an application of this thing. So the interesting part is this is more than just redundance, because it's software redundance. Yeah? It's not just two processors doing the same thing, storing the same thing, but there are also two programs doing the same thing, but they independently. Yeah? Okay, this can be a good idea, but it is very limited in its range of application because the programs have to do the same thing. Yeah. Okay. So what is then more useful for the applications we have in mind is the SIMD architecture, which is doing things like this. So two processors or more, two or more processors, processor 1 and processor, say, n, up to n. So they are dealing with the same data. Okay, they can actually work on different parts of the same data, but they are run by one program. So there's only one program and two processors. This is the vector, it's called the vector architecture. So nowadays, in the 70s, when they made this list, there were big machines that were vector machines. Nowadays we have these vector machines. In particular, we have them. So where do we have a vector machine? In a GPU. And usually the processors also have vector units, nowadays. Vector units. So this is something that we really have to care about because this is where the big computing stuff now goes on. So no artificial intelligence without vector processor. Yeah. Nowadays they call them tensor processors, because they have big vectors in a sense, but it's the same idea. Okay, so this is something important, and there is something else that is important and that we have to care about, and actually in this lecture we will mainly care about this thing. So we'll basically do two things. We do a little bit of SIMD and a lot of MIMD. This is where we have so we have this big data as probably okay. I mean, I think the picture I draw is maybe a little bit. Okay, let me correct this. I mean, because yeah, they may be in the same memory, of course, but the data is separated. I misdraw this. Yeah, so the same here. We have multiple data. We have multiple data, and we have so this multiple data can be still accessed through together. So data. I put a box around this to make this clear. Processor 1 and processor N. And here is a program 1. And program N. So this down here, they look pretty similar. Gesundheit. They look pretty similar to the single instruction, single data. Yeah. The only difference is that they can also access, that the data does not necessarily has a boundary, so they can cross-access some data. Yeah. Okay. So this was the. This has been the. To have a new page. New page. So if you have not seen this. So these are the classifications. And now we have to introduce a few basic terms. This is again so that we are on the same page. Maybe you are already familiar with this, but we have to make sure that we all understand the same things. Maybe I have a few terms that you know and a few terms that you don't know. So basic terms in parallel computing, or in computing in the first place, say we will use the word core. A core for us will be an arithmetic sometimes called arithmetic logical unit. I just called it arithmetic unit plus the control unit. This makes up a core, and this is the stuff that conducts floating point and integer operations. Basically, it's what back in my youth we would call this a CPU. However, nowadays the terms are a little bit shifting, yeah, because nowadays we still call the big thing that you put into your computer, we call this a CPU, and this thing has several cores. Yeah? Previously, one CPU, one core, now one CPU, several cores, obviously. So the CPU, this is the central processing unit. What we call CPU. Yeah, just to make clear, with the CPU we mean the entire thing. Basically, this little black something that you put into your computer. This is what we call the CPU, and this will have several cores. So this is the main processing unit. In a computer. And nowadays they would typically have several cores. Okay, they will have several cores, and they will also have several caches usually. So we'll come in a minute to what is a cache. Right now we come to what is cache. So this was central processing unit. Then we have our cache. Okay, we can give an entire lecture series on what is cache. So just the basic definition. So the cache is a fast indexed memory. And this keeps copies of the data in the main memory. Copies of this is why we need to index it. Yeah, so it's not just the data, but it also says so this data is a copy of this place in memory, right? So one thing that we already had is RAM, as you correctly said. This is random access memory. This is the main memory. Of a computer. And then we have the bus. And the bus is a data transfer mechanism or system. So you will have probably several buses in your computer. For example, the mouse is also connected to a bus because there's a data transfer between the mouse and the computer. But what we usually mean is the thing that transfers data between the RAM and the CPU. So this is the important bus for us. Let me see now. And it typically consists of several lines. I think that USB consists only of one line, at least it should according to its name, right? So because hello. So you can have a serial bus. Serial bus means data is transferred one after the other. Yeah, and parallel bus means several lines in parallel that can transfer several bits at the same time. So the data bus between your memory and your and your CPU is of course not a serial bus. This would be much too slow. So they have many lines usually, or according to the width of your processor. If your processor is a 64-bit processor, then it would have 64 lines, yeah, in parallel. So I guess this is all nothing new. Maybe now it's getting a little bit more interesting. So the bus width, this was just what I have just mentioned, is the number of parallel lines. So this is what they mean when they say you have 64-bit bus, then it means there are 64 lines in parallel. And then, so this is an important thing for us, and another important thing for us is the bandwidth. Okay, don't mistake bandwidth with bus width. Bandwidth is something different. This is the data throughput of a bus or a network and this means it's the time. I switched the line, sorry. So the throughputs in bytes per second. So usually it will not be in bytes per second, but will be in megabytes or in gigabytes per second, right? So this is of course related to the width, but it's also related to the frequency with which data is transferred. Yeah. So that the broader the width, so it's basically the frequency times the width is the bandwidth, right? Okay, so you're familiar probably with this, and then there is the latency. Latency. What is latency?
How much program has to wait to transfer something?
Yes. Yeah.
You get a response.
It is the response. It is not. It's a bit. The response time is a bit more. Okay, it's basically almost. Yeah. It is the time between you're asking a question and the response starts. Yeah, because the response time would be you ask for more, you have to wait longer, obviously. Yeah, but it is only the gap in between the question and the answer. So this is the. Actually, I have in my script I have response time here written. Yeah, but I wanted to. So it's the response time of bus or network, but we get it a little bit more specific. So it's that is the time between the query and the start of receiving the answer. So, okay, this is important because it's not including the transfer time of the data. Okay, so then I probably start on a new page. You know, the guy who is responsible for the computers just before the lecture complained to me that the students always come and pull out the power plug from the computer.
Yeah.
So sorry, I'm the bad guy because I had to use this.
Yeah.
Otherwise,
Don't worry.
maybe you go. You see the guy behind you. There's one. Yeah. Okay, so let's look at what we call a processing node. Processing node. This is a unit of one or more CPUs with shared memory. Actually, this is what we would usually call a computer, but see, suppose we call this here our network, and here comes a box where we have a CPU which may have several cores or not. So there's cores, core. Okay, this is a CPU, and they together have a common memory. Basically, you could think about this machine here being, something like this. And then there is another one that may look the same, or usually look the same. So they are together in a CPU, and then they are connected to RAM. So the thing with the compute node, so this is, a processing node, compute node, processing node. Say this is processing node number 1, and this here is processing node 2. Yeah, so the thing is that each node, in each node, there still may be several processors or still be several cores, but they all share the same memory. Yeah, and between two processing nodes, they do not share the same memory. Yeah, so obviously for these two cores, it's easy to get into this RAM, but for these two cores, it's not easy to get into that RAM. Yeah. So, and the entire thing here is what we'll call a cluster. This is a combination of several compute nodes. Okay, and this is also what we are going to use in our exercises. So, computing power is another term that we have to define. So the computing power is a maximal number of floating point operations per second. Okay, so there is, I always have a little bit problem writing this down. Yeah, this is flops, so this is a capital S. Yeah, you're nodding. What is it when it's a small s? Don't know, yeah. This is a little bit, okay, so they could be multiplications. Let me finish this and then I come to this. Or additions, usually. Okay, so unfortunately, the literature is not absolutely consistent, or at least not with physical units. Yeah. So you could also write this as floating point operations per second. I would actually prefer to write it like this, and sometimes it's written like this, but it's more often written this way. Because what they sometimes mean when they write flop with a small s is multiple floating point operations. It's not per second. Yeah? And this here is supposed to mean per second, floating point operations per second. How fast is this growing with each year for a new machine? 75%, yeah? So the compute power is growing 75% per year if the number is correct, which comes from some place, I don't know. But for solving your actual problem, it does not necessarily grow this way. It may actually grow only 25%. Yeah, because if you have data starvation, yeah, so if you are limited by your bus, then your actual compute power is growing much slower than what your compute power could grow like. And in order to make your programs actually take advantage of this, yeah, you have to really think hard, what do I have to change in my program so that I can take advantage of these things and not starve of data. Okay, I have two things that I wanted to add here. So when we talk about floating point operations, then we have to define what is a floating point operation. Modern computers are able to merge, at least sometimes, able to merge additions and multiplications. So an addition together with a multiplication would only be one operation. And then there are operations that may be more expensive, for example, division. And of course, things like square root, and others, they will be more expensive than a single floating point operation like an addition, or expensive than, say, multiplications. So additions and multiplications have the same price. Okay, sorry, we have to have a few more terms to define that you probably already know, but anyway, what is a thread? No? A thread like, no, do I have take my clothes apart? No. Yeah, it's a process. We'll have process is the next thing on my list.
Like a stream of instructions.
Yes, right. It is a sequence, yeah. It's a sequence of instructions, and they are independently. So they're independently executable string. I mean, independently of other.
Yeah.
This is threads. Independently executed sequence of instructions, and we actually know these things from sequential codes too. So actually, threads were there before we had parallel computing, and usually on your machine you will run more threads at any time than you have processors or cores. I mean, yeah. So they do more or less the opposite of parallel programming. So you have several this is multitasking, right? So you have several threads, more things to do than you have actually cores that could do it. So you will pause one of the threads and do something else and go to the thread again. Yeah. So this is multi-threading, and the multitasking actually. Yeah. And now, in parallel programming, we are more interested in the other things. So how can we do things in several of these threads in parallel that potentially are together in the same process? Yeah. So because a process or a task, and we call this also task. Would be an instance of an application with at least one thread. Now, modern applications usually have several threads running either in parallel or switching between these things. Yeah. So one is taking care about the background saving stuff. One is taking care about the whatever. The user interface, yeah, all these things are several threads. So, okay, now I need another page again, and now we come to something a little bit more concrete. Namely, we look at a single instruction, multiple data program flow. So now this is related to the threads. Say we have the program. but what we've written here, so there was process and task.
Oh, okay.
Yeah, sorry, yeah.
I didn't come up with the definitions and things.
Okay. Now we look at how single instruction multiple data deals with different threads. So the idea here is, since we have a single instruction, we have still several threads because we have several threads working on different data, but the threads all do the same thing, right? So, and say the program would be something like this. We have, say, if query Q, then do A, else do B. Okay, very simple program. And this will now be executed in several threads. Okay, let's say there would be a thread number 1. Thread 1 will be thread 2 and the thread 3. And say we are looking in this direction will be the time. So, and here's the instruction if Q. Okay, so if Q is of course a branch, yeah? So you do either the one or you do the other. You have several threads that are supposed to do the same thing. So how can they do the same thing if they have a branch? Because in principle now, what you could have here is that they say that it would be true here, would be true, and here would be false. Yeah? So this would mean that threads 1 and 2 would have to do A, and thread 3 has to do B. Right? So how does it work in this? We'll have here do A, then we would have an else, and they have do B. So what now happens is that if I take a line here, say I do this in green, so they work here, yeah? So they do something while this guy here just does nothing. And then after this guy will do B, while this is not doing anything and this is not doing anything. So this here would be wait, and oops, sorry. This here would be execute. Okay. This would be execute. Okay, so this is important. This is important to know. Because you see, you can, even though you have a single instruction, multiple data architecture, you can still use branching in your code, yeah, with if-else, but the way this will be executed is they will simply execute both, and during the time when for these threads for which the condition is false, this thread will just be turned off. So it will be turned off, it means it has to wait. Yeah? So the time you need in this way of programming, the time you need to execute a program with a branch is always the time it needs to do both. And of course, if you have lots of, nested branching, this can get very, very long. Yeah. So this is something that we have to keep here in mind. So here, yeah, in SIMD, we are using threads. I should write this small. So the threads have independent data, but the same instructions. So you don't have this condition, of course, in MIMD, where you have where the threads have both independent data and independent instructions. So it will execute only the condition that holds. So they will not have to wait. So the other threads don't have to wait for the ones that has to be executed. How late is it? We have another quarter. Yeah, so in what we still have to introduce here is the difference between shared memory and distributed memory. This is one thing that I've just addressed a little bit. So say shared memory looks like this. So there's a processor, which I just processor core, yeah. So for example, you could have also two CPUs. Now I just write P here for processor. There's a bus. They are both connected to the same bus. And then there is a common memory. If you have a machine like this, your programming strategy would be to use shared variables. So you want to write a parallel program, two processes working on the same thing. The way you parallelize things, or the way they interact with each other, is they have access to the same variables, right? Because they are in the same memory. This is possible with shared memory. You have to take care that the simultaneous access to the same variable is not allowed in this model. So there can be a clash. And then we have distributed memory. Where we have processors, or there could also be several processors, but never mind. There would be RAM bus in between. And they are usually connected now with a network. So we have these compute nodes that we had already had before. Here we have a network. And now you want to make these two guys to work together. Here, it is not possible for the compute node on the left side to just access the same variables as the one on the right side, right? So what you have to do is you have to make the two of them talk to each other. Yeah. So one they are sitting on the same, the other one they are sitting on the same table. Yeah. They work together. They just they look up. So what has he done? Yeah. What has she done? Yeah. And here they are separated. They actually have to send out data and collect data. So here the programming model is message passing. And this is also, we will do both, but we will spend more time on the message passing than we will do on shared variables. Okay, since we have 10 minutes left, I'll end this lecture with a few more terms that we wanted to introduce. For different machines. So there's UMA machine, which is called Uniform Memory Access. Uniform memory access means it has the same it needs the same time to access any place in its memory. So all memory requires the same time to access. And then when there's uniform, then there's of course non-uniform. This is called NUMA machine, which is just non-UMA. And this means that access time depends on location. You see, my access here depends on the location of my hand on the screen. I cannot put this to the other side. So actually, this is pretty common, yeah. So you can imagine like this: if you have a CPU and you have one core here, so sometimes you have more than one CPU in your computer. We will probably also have some cache in here. So you may have configurations like this. Another CPU with another core, cache. So they are both connected to the same bus. And here we have some RAM. So is this NUMA or UMA? Yeah, maybe Mr. Kutsche is helping me if I'm saying nonsense here. So it is even though they are connected to the same bus, they may not be accessing all the memory at the same speed, because they are accessing it through different caches. Yeah, so if something is already in the cache in this processor, it can access this here faster than the other one. Yeah, but it can be actually worse than this. So okay, you say this is NUMA. No, Konstantin, is it NUMA or KUMA? No, I was, by the way, I was not pointing at you, I was pointing at the guy behind you. It's NUMA because it accesses the memories for different cache. Yeah, but it can be, so but it can be even worse than this, because you can, most machines nowadays look like this. Say we have internal cache here. Yeah, you would have several levels of cache. Yeah, okay. If you have several levels of cache, then even within the different cores can have different access times, because they are connected to different levels of cache. So first level cache will be connected to one core, and third level cache will be connected to all the cores. Yeah?
Like one outside the chip, I think. It's like 3 levels nowadays.
No, even the third level cache is inside the chip. Yeah, but there is something outside the chip too. Say we have a machine like this, where we have, sorry for this nonsense. Okay, sorry for this nonsense too. So say we have a machine like this, and then what we often have is we have a separate bus for this, and this is going to this RAM, its own RAM. So how can these two guys actually communicate? Oh no, I made a problem because I now don't have space in between them. Let me try to draw it like this. Yeah. So there is something that we call a bridge. Which means so I have to avoid okay, nobody is looking. I can move the whole diagram. Yeah, that would be that would make sense. Yes, I should move the whole diagram probably below. You know, you're implying that anything works here. Oh man, go on. I think I cannot move the whole diagram. Okay, let me just finish here. So there's another bus, and it has its own RAM. So several processors will be organized like this. Maybe nowadays more. So if you have a computer with 2 processors, yeah, on your main board, then there's a possibility that they are not all the same, but there's a possibility that both processors have their own memory bank, but they can still access everything because they have a bridge in between. So the one processor is accessing the memory from the other processor through this bridge. So it's not going through the bus, but it's actually accessing the other processor, and it's going through the bus of the other processor. This is, of course, a longer way than going to its own memory. Yeah? And therefore, this is also, this is clearly NUMA, because accessing the memory in the other memory bank that is not associated with your processor yourself will take longer time. And okay, maybe I'll, because I have a minute left, I just finish up by saying that there is different ways of doing this too. There's a cache coherent NUMA, which we call C NUMA. And this means that data in cache is always kept valid across the different processes or different cores. And this is, of course, more expensive, so there's an overhead associated with this. So then there will also be non-coherent NUMA. This is something that's not taking care, so it's not safe to access variables that your neighbor may have changed. Non-coherent NUMA. Okay, so with this, I think, Koma, I will continue next time because we have now 11:15. I will try to, okay, it's not possible. No, it's not possible. I will try to stop the recording if I manage to. Yes.